In this video, we'll be looking at one more type of radiation and talking a little bit about how that radiation actually interacts with your body before doing some examples of some transmutation reactions just to kind of give us some practice. So, in the previous video, we talked about alpha radiation, those big, heavy helium nuclei that are charged. We talked about beta radiation, the negatively charged ejected electrons, the beta decays, and then even electron capture. And in all of those, we are dealing with charged particles. With gamma radiation, we're not actually dealing with particles at all. In fact, gamma rays are just pure energy, high energy electromagnetic radiation. And where we see them most often is in what we would call annihilation collisions. So you've got a beta particle that has a negative charge, a positron which has a positive charge, and when they collide with each other, they basically annihilate each other. They come out, and it's just a pure energy release. The resulting particle has essentially no mass and lots of energy being emitted. And so, where we tend to see this most often are inside of stars, and as a result, gamma rays are very common in outer space. And for the most part, we're protected from them by the gases in our atmosphere. However, when we do have earthbound gamma radiation, um, it is quite damaging and it is quite powerful. It can disrupt cancer cells, it can disrupt regular cells. It's just very um, damaging overall because of its high energy. And so if we look at the penetrating power of those three types of radiation, alpha particles, because they are so big and blocky and dense, they're actually very easily blocked. Your own skin, your clothing, paper, cardboard, those kinds of materials can block alpha radiation relatively easily. The only real dangers with alpha radiation are if somehow you ingest an alpha emitter. Um, it can have lasting effects on your internal organs. Also, if you have broken skin, obviously the alpha particles can make their way in through your broken skin. But even at that, it's still difficult for them to actually get into and do significant damage unless they actually get inside of your body. Beta particles, on the other hand, are able to go through that outer layer of skin, your epidermis. Um, Materials like paper provide some protection. Usually we have to go to a little bit more dense. Certain thicknesses of aluminum are capable of blocking beta radiation. Um, the danger with both of those is because the particles are charged, they are what are called ionizing radiation. That means that as they interact with your skin, as they interact with your organs, they steal electrons from them. And the de-electronified uh, cells become much more dangerous. They can either die, they can mutate as a result of trying to undergo chemical reactions to replace the electrons that they lost. Lots of different things can happen. Gamma rays are the most penetrating. They have the most damage potential. They are also ionizing radiation. But because of their low density, because of their high energy, you need either lead and a decent thickness of lead, or a even thicker dimension of concrete to actually block gamma rays and other kinds of high energy radiation. And so this is just kind of an illustration of that. You can see that alpha radiation is actually stopped by this outer layer of skin. Beta is capable of going through that outer layer, but usually gets stopped in the interior layers of tissue. Gamma goes all the way through everything. So let's take a look at a couple of examples of transmutation reactions just to get into the feel of how to actually go about balancing these. So for example, polonium-218 undergoes both alpha and beta decay. Write balanced nuclear equations to describe these reactions. And so We're going to look in both cases here. We're looking at polonium-218, so our mass number is 218. Polonium on our periodic table, and atomic number 84. All right, and so in one of these scenarios, it's going to undergo alpha decay. And so alpha decay, we're going to have a mass number of 4, atomic number of 2. And so the other particle here is going to be kind of what's left over. So remember, our law of nuclear conservation says our mass number needs to be conserved and our atomic number needs to be conserved. And so I had a mass number of 218. 4 of it is spoken for here. The rest, 214, must be here. And I had an atomic number of 84. 2 of it is spoken for here. That gives me an atomic number of 82. I look on the periodic table. Atomic number P82 is lead, Pp. And so that is my nuclear reaction for the alpha decay. Now for the beta decay, let's pull out a different color here. I'm starting at the same exact spot. Polonium-218. The only difference is instead of an alpha particle, I'm going to get a beta particle. Beta particle has no mass and a -1 charge. Looks like a funny kind of elongated B. Law of nuclear conservation here again. 218 was my mass number. 0 of it is in the beta, so all of it must be in the daughter nucleus. 84 was my mass, or excuse me, my atomic number here. I have a -1 here, which means I'm actually going to have a step up, 85 as my atomic number there, and responds to astatine, AT. So that's how you do transmutation reactions. Let's take a look at another example. All right, in this example, we are actually given the parent and the daughter nuclei, and we need to figure out what they form, what the nuclear processes are. And so, again, a good time to have your periodic table out and handy, because you're going to need to look up what these are. So with actinium, we have element number 89. And with francium, we have element number 87. And so again, keeping in mind our nuclear conservation here, we've got 222 as my mass number, 218 is the mass number of my daughter nucleus, 222 minus 218, that gives me 4 left over. 89 minus A is 7, gives me 2 left over as the atomic number. And I would get helium for this. And so this tells us that this is an alpha decay. In this next one, I've got vanadium. Vanadium is element number 23, and titanium is element number 22. And so we can see here, this is an interesting situation where we actually have a daughter nucleus by itself on the product side, and we need to do the calculations on the reactant side. So 47 is my mass number here and here, which means that I've got no mass. 22 is my mass number here. 23 is the mass number, or excuse me, the atomic number here. And so I would need a -1. 23 plus -1 gives me 22. And so we can draw this a couple of different ways. We could draw this as a beta particle, or more commonly, we draw it as 0, -1, and call it what it is. This is an electron. And so this process where an atom grabs an electron is electron capture. Okay, let's look at two more examples before we kind of close this up. Radon decays with a loss of 1 alpha particle. Let's look at the radioactive decay for this one. So I've got 222 radon. Radon is number 86. And it's undergoing an alpha decay. So we already know that 4,2 alpha is one of the parts. So what's left over? I've got 222 minus 4 is 218. 86 minus 2 is 84. And I believe we saw this previously. This is polonium. In this last one, we have the beta decay of tritium. Tritium is an isotope of hydrogen where the mass number is 3. So I've got 3, 1 hydrogen, and it's undergoing a beta decay. And so the beta, 0, -1. And if we look at the product of this, 3 minus 0 is 3. 1 minus -1 is 2. And so what we have here is an atomic number of 2, that's helium. The resulting nuclide here is a helium nuclide, helium-3. Now this is actually still an unstable form of helium. It's going to undergo another decay along the way. But this is definitely more stable than the tritium was. So let's close up our look at nuclear chemistry by talking about one final concept, and that is the idea of a half-life. Half-lives are a way of measuring something that we call kinetics. Kinetics just means how fast a reaction proceeds, how fast a reaction goes. And half-life is the amount of time it takes for half of a radioactive sample to undergo its decay. And where we find that particular idea useful is when we talk about nuclear decays, half-lives are actually repeatable events, meaning that every single half-life is the same length of time for a nuclear sample, regardless of how long or how much of the nuclear material is present. And that's an important thing to know because that means that it's predictable. You have a good sense of knowing how long it's going to take. And so one thing that we can look at is this relationship here, where we can measure, okay, how much of a nuclear sample is remaining and how many half-lives have passed. Because if I know that I have 30 grams that I started with, and I'm looking at the sample now and saying, okay, I only have 7.5 left. Well, 7.5 is 1/4 of 30. And that means that 2 half-lives have passed. And so I just take that length of time, whatever the half-life is, and multiply that half-life by 2, since 2 half-lives have gone on. And where this is really, really useful is in something called radiometric dating. Radiometric dating is used in a number of different fields where we are able to determine the age of artifacts, especially organic artifacts, based upon the amount of carbon-14 that is present in the artifact when we find it, and comparing that amount of carbon-14 to the amount of carbon-14 that is in a normal living creature. And so this is the primary means that we use for determining ages of things. And since the half-life of carbon-14 is somewhere on the order of 5,700 years, we can get a pretty good sense of how old things are based upon the amount of carbon-14 that's present. So this closes for us our unit on nuclear chemistry and radioactivity. Until next time, have a good day.